So, one more thing to discuss is what's known as Fischer projections. Now, up until now, we've talked about 2D structures. This is where we're looking at this, and we use things like wedge and dash notation to denote or to show the geometry around an asymmetric center. Other projections, remember we've got the Newman projections, we've got the chair projections. Those are used specifically for conformations in our things like cyclohexanes. Fischer projections is just a different way of viewing tetrahedral centers, specifically asymmetric centers like we're showing here. And these are typically used in things like biochemistry, specifically looking at geometries of things like sugars. This is a really common thing that's used for that. So in a normal 2D wedge dash rotation, what we're doing is we're looking at a structure like this where these solid lines here denote that they're in the plane of the page. A wedge means it's coming out of the plane, and the dash means it's into the plane, but we have some atoms aligned in the plane of the page. We move to a Fischer projection. What we're going to do is view down this bond at this carbon. We're staring at that central atom. So if we look at it here, what we're saying is that, say, these atoms are in the plane. That means that the green is towards you, red is away. What we're going to do is stare through this point. So imagine if you put your forehead on the asymmetric carbon. So we're looking at it like this. The two bonds side to side, the green and the red, are towards me, and we place the other two, top and bottom, away from me. So we're like staring in that sort of space in between. So what that does is it'd be like changing the perspective to look at the cross like this, where we have the two bonds away from us, the oxygen and hydrogen are towards us, and then we abstract that down in Fischer projection as this cross. We drop all lines into this kind of a flat type projection. So let me show you what this looks like on the side cam for just a second. So there you go. So if we take our tetrahedral center, right? So in the normal one we've been talking about, let's say the blue and the green and black are in the plane of the page. This would be sort of our tetrahedral presentation, where gray would get a wedge, red would get a dash, blue, black, and green are in the plane of the page. For the Fischer projection, what we're doing, first of all, is you're examining it in this kind of perspective, right? We're staring at that middle black carbon where the blue and green are away from you and the red and gray are towards you. So you're staring at this middle one where in the top, the up and down axes, those are going to be away from you, and then these two, gray and red, are towards you. But we give it that sort of plus-like sign. You can see there, we're abstracting this in the Fischer projection. We're left and right, up and down. We give this flat type of presentation, but the convention we're trying to denote here is when we represent something in Fischer projection like this, that's a central carbon, these are towards you, these are away from you. This is a simplified version at this point. Now this is usually used in things like carbohydrates, long carbon chains where we've got multiple chiral centers as you go through this. It's one more visualization that's necessary, and it's very important when you start to see these things in certain biochemistry. It has some value in particular with certain kinds of presentations. So here in Fischer projection, the vertical bonds up and down, those are denoted to be into the page. They're both dash. Any horizontal bond in this one side to side is out of the page. That's going to be wedge. Okay. So here, the Fischer projection shown on the left-hand side, the nitrogen, hydrogen, those would be away from you. The methyl and ethyl is towards you. So that one Fischer projection, usually, again, we set it up in this convention where we have a very specific sort of orientation like this. That would look like these three 2D wedge bond structures. This is where we're taking that same molecule and we're rotating it in different perspectives to show you that. So just something to practice through. Take that structure as drawn and then just practice rotating or manipulating it. Every one of those three 2D structures corresponds to the same Fischer projection. The way you would see it really depends on sort of orientation. As you notice here, nitrogen, hydrogen, we want those in those vertical positions, so we need to look, for example, at this specific geometry. Nitrogen and hydrogen would both have to be oriented away from you. That would put the methyl and ethyl towards you. You would have this specific perspective here. When the values of something like Fischer projection is we orient it where, again, specifically nitrogen and hydrogen are up and down, and with that particular geometry, we are locking in the possible different perspectives into this one particular geometry. We're saying that it has to be oriented in such a way. The nitrogen and hydrogen are pointing away from you in this kind of up and down perpendicular kind of axis. So CIP rotations like this are a little bit different, but again, follows the exact same sort of things that we've seen so far, or the same rules for R&S assignment that we've done with our normal 2D. The just thing you have to remember is where the groups are. So the priority rules don't change. The only thing you have to look at is, depending on the structure, the lowest priority group may be towards you or away from you, depending on what position it's actually around here. So for right now, step one would be to take a compound like this, assign the CIP rules. If the lowest priority group is on the vertical axis, remember, if it's along the side to side, that means it's facing you, it's towards you, in which case it's the opposite rotation, assigning it. If it's on the horizontal axis, vertical axis, up and down, it's already away from you, you assign it like normal. If it's on the horizontal axis, side to side, it's towards you, you have to look at the reverse rotation. That's the opposite one, where the lowest priority group is already facing you. You are looking at it from the wrong side. You need to reverse the molecule as we do that. Okay, so we're going to practice that on a couple of these sort of examples over here. So, excuse me. First of all, for this one, as drawn, we have our Fischer projection, COOH, OH, hydrogen, and methyl. Now in this one, remember, if we assign these, that's going to be number 4 for sure. Oxygen is number 1. We have our 2 carbons. The carbons with the oxygens will be number 2, and this is number 3. So as it looks right now, you can see, okay, 1, 2, 3, that looks like this is the rotation goes from 1 to 2, skipping over 4 to 3, right? So 1, 2, 3 looks like it is an R rotation, right? It's clockwise. But remember, lowest priority group is here on this hydrogen. It's on this horizontal axis. In the Fischer projection, that would be like looking at this center here. The hydrogen is currently towards you in that perspective, right? It's towards you in this point. So since the lowest priority group is on the horizontal axis, it looks R. This is actually S. The nice thing about Fischer projections as far as rotation goes is it follows exactly the same rules that you've done, but there's really these only 2 outcomes. If it's along the horizontal presentation, you assign it, reverse it. You're looking at the wrong side. Lowest priority group is already towards you. If it's on the the vertical axis, up and down, it's already away from you. You assign it like normal. You're fine. You don't have this third possibility of it being in the plane of the page, just based on how the Fischer projection is actually done. So how we get to Fischer projections, how we convert between the two. This is one of those, again, it's a conceptual point that you can work through. One way to do this is imagine, first of all, given our 2D line bond structure, you imagine looking at or placing that at the center that we're looking at. So imagine picking up the molecule, and what we're going to do is stare at the asymmetric center that we're going to be drawing, and we place it in such a way where we're looking directly at this bond. We want the other 2 bonds in the vertical axis pointing away from us, and we have the other 2 reaching towards us like a hug, right? So we're going to do this step by step on the molecule as shown here. This is just shown out diagrammatically, sort of the direction or the position we're supposed to sort of view it from, and then step by step what to do. All right, so if we had, let's say, this molecule here as drawn, OH, and that means going in the back of the page, there's a hydrogen. What we're doing is viewing the asymmetric carbon from such a position that these 2 groups are going to end up, they're pointing away from us. If I'm looking at it from that arrow, so they're flying above that sort of position, if I'm looking at this carbon from that upward position, I'm positioning these 2 groups, the methyl and the carboxylic acid, away from me, which means when I transition over to my Fischer projection, these 2 in this kind of presentation here, up and down on this axis, these would be also away from me. So I'm going to position it where the carbon I'm staring at, the one here in the middle, is at this position right here. And if I'm staring at that carbon, so I'm imagining like turning to the side, looking down at this position, the methyl group would be up here at the top, the carboxylic acid is down here at the bottom. And what I'm saying there is, again, they're facing away from me if that atom was, that central atom was sort of looking at me. This is also back to imagine again, it's like when we do Newman projections. Imagine you're grabbing the oxygen coming out of the page with your left hand. you're grabbing the hydrogen in the page with your right hand. I'm picking up the molecule and I'm placing them, the oxygen and hydrogen, to either side of my head, right? So what I'm doing is I grab the oxygen coming out of the page with my left hand, I grab the hydrogen back into the page with my right hand, I'm picking them up and I'm holding them this way, side to side along the horizontal axis. I'm holding onto those two, which puts the carbon chain up and down along the vertical plane. Horizontal axis got the two groups either side to side to an asymmetric center. So if I grab the oxygen with my left hand, hydrogen with my right hand, I'm holding them, I'm looking at that sort of bond right in the middle. These two are coming towards me, and more importantly, when I draw my Fischer projection, the OH will still be on the left-hand side. So I have my cross, OH is over here, hydrogen is over there. One thing you can always do to double check if you've drawn the conversion properly is assign this center, R and S, and here, R and S. If you've drawn everything correctly, the configuration should not change. So right here, 1, 2, and 3, as drawn, this is an R center, right? Hydrogen's to the back. If we go over here to our Fischer projection, once again, 1, this is 2, and this is 3. It currently looks, 1, 2, 3, looks like it's an S center. Remember, the hydrogen is along the horizontal plane, is coming towards you. This is actually an R center. So we've done this correctly. It's R in the 2D structure, it's R in the Fischer projection also. Okay? So, as we convert this through, when we have multi-bond structures, and this is where we have multiple asymmetric centers, what we need to do is actually convert it, the conformation of the molecule we're considering, into almost like a curl. Now this is typically used, we use Fischer projections for these long carbon chains. We have a linear carbon chain with potentially multiple stereocenters. Every time we have a cross in one of our Fischer projection, every time we have one of these, that's referring to a tetrahedral carbon. Usually it's one of our centers, and we're using this specifically to denote the stereochemistry at that asymmetric stereocenter. But every one of those crosses is one carbon in the chain, right? So if we take the molecule that we have on the left, originally this nitrogen and this methyl group are on my asymmetric centers, and then I've got this ethyl group down here at the bottom. The first thing I need to do is I can't look at this structure as this extended, that's our normal staggered structure we use in our line bond. When we're talking about Fischer projection, we need to sort of roll it in such a way that every one of the, like if we're moving down the carbon axis, I need to roll it in such a way that every one of those bonds has the same general presentation I just talked about. The two groups side to side must stick out towards me, right? So in this case, both groups that are on the horizontal plane must come out towards me, and that puts the carbon chain along the middle here. What actually that means is I need to take my carbon skeleton and actually point it so that it's in sort of like an eclipsing architecture. The conformation I'm looking at it is going to have it bent around on itself. So let me quickly show you what I mean by that. Okay, so I'm just going to, with my model kit, build this kind of structure. Hold on right here. Need one more carbon. Okay, that's okay. We'll do it from like this. All right. And let's go over to the side cam. Okay. In Do it live. We'll do it live. Okay. All right, so the structure that we showed on our slide can be represented by this molecule here. The nitrogen on carbon 2 is coming towards you. It's a wedge. Hydrogen is a dash. Next carbon over, we have a methyl coming towards you. When we have it presented in this way, this is our zigzag type pattern, and we have an ethyl down here at the end. Okay, so that's our 2D, that's our three-dimensional structure from the 2D line bond structure. Now, what we're going to do is we have to sight on this carbon and this carbon. Remember, the direction we need to sight on it is such that you look at this carbon, putting the carbon axis, the long bond chain, right? The carbon chain here is going to be in the vertical plane, and then these two groups, either side of it, must be in the horizontal plane. So there's two things we have to do. We're going to turn the structure, and we're going to look at this carbon here as my Fischer projection. So if you see that right now, that carbon here, along the vertical plane, we've got our carbon up at the top, the methyl, there's my asymmetric center, and then that's the next one in the chain like this. That puts the nitrogen over on my left-hand side, the hydrogen on the right-hand side. That's that first point. Now if you look at this next one, the problem is if I don't bend it, if I look at here, and I was going to sight on this carbon directly, one thing you notice is, okay, the methyl, the carbon chain up here, and this carbon chain down there, those are coming towards you, right? Those are presenting towards you this way. The other two groups, the methyl and hydrogen, are away from you right now. That is not Fischer projection. That's not the right point. We would actually need to sight on this carbon from this direction, right? We need the two groups on the horizontal plane coming towards you. We need the carbon chain, the chain that's on the vertical plane, going away from you. So one way to think about that is if this is our conformation in our 2D line bond structure, what we're really doing is we're rolling it so that all the carbons we move down the backbone here, all the carbons we move down the backbone are presenting, so all the groups at those asymmetric centers are commonly side to side. That way when I look at it like this, I'm looking at, first of all, the first carbon here. So this first carbon right here, if I look at it from the top, I've got my nitrogen, my hydrogen, my carbon, and my carbon chain. That's as we drew before. So the Fischer projection would put the nitrogen on the left-hand side, hydrogen on the right, and then the methyl and the rest of the carbon chain pointing down. If I move over to the next carbon, this one right here, it's already presented now side to side along the horizontal plane. These are coming towards you. The carbon chain along the vertical plane is facing away from you. So now we can see hydrogen is on the left, methyl is on the right. And then the last part, this ethyl group here, since there's no asymmetric centers over here, we don't need to draw these in Fischer projection. We're only using it to denote the geometry of these two asymmetric centers in my point. And that's why in the line bond structure, it's actually an eclipsing one. We roll it around on itself because it allows us, when we go to Fischer projection like this, top and bottom, they're both away from you. Here, again, top and bottom, they're both away from you. These groups, side to side on the asymmetric center, are pointing towards you. Okay. So that's the difference as we sort of move through this point. In line bond structure, we typically draw things as an extended, staggered sort of one. We talk about Fischer projection. It's like you're taking the carbon chain, whatever that's sort of that along that long vertical axis, is set so that they're sort of curled back on themselves, and then you're sort of looking at each one of these centers as you move around, where things to left and right are pointing towards you all the time. The things on the bonding chain that's sort of moving down is always pointing away from you. So it has this kind of bent around sort of architecture. It doesn't represent the most stable conformer, but it's easier to sort of pin it into this one to give us our Fischer projection. So that's why we end up this transposition as you see right here. You sight on this first carbon from the top, effectively, to give you nitrogen on the left, hydrogen on the right. What you could also do is think about looking at this next one. I need to sight from the bottom here, this methyl. Now put the methyl on the right, hydrogen on the left. Or twist this ball around, look at from this conformation, then you're sighting from this side, from this side down here. Always putting those two groups flanking you from whatever your perspective happens to be. Okay? So, working through something like this, though, once again, in order to draw these ones, and this is where I'm going to do this one on the iPad. If we had a molecule like we've shown over here with this aldehyde, to the back right now is our methyl group, and over here chlorine and carboxylic acid, COOH. So this is sort of in our normal sort of geometry. This is how we would do this, where we've got a staggered kind of geometry where the carbon chain extending through kind of has this, the zigzag that we're most familiar with. Once again, I would have to cite on this carbon from this direction. I'm looking at this asymmetric carbon. Again, if you were to sort of imagine drawing this out, I would start by drawing my straight line. I have 1, 2, 3, 4 carbons in the line. On the top, I have my my aldehyde, COH, right? Or I could draw that as the aldehyde itself. The carbonyl explicitly shown as a double bond. The next carbon in the chain, I draw a cross. Next carbon in the chain, draw a cross, right? So that's denoting this guy and this guy next. And it's terminating with a carboxylic acid. So the first thing I do is I line up my chain in this way. So I'm drawing my aldehyde from the top to the bottom. Actually, I think I'm going to specifically draw this out so we can see that clearly. This is a aldehyde like this. That's the carbon up at the top shown here. Okay, so carbon number 2 in this chain has a methyl group on it. I'm citing on it from this sort of direction. If I do that, you notice that the 2 bonds along the axis here, those 2 bonds are already pointing away from me in that position. So this would be like reaching to the page, grab the methyl with my right hand, the hydrogen pointing out with my left hand. I'm picking it up and I'm staring at that middle carbon. That puts the methyl group over here, hydrogen over here. Now moving to the next one, I have 2 options. Do not look at it from this position, right? Because what's happening there is the carbons here are actually pointing towards you from that one, as long as we have it oriented along that axis. If the carbon chain is along the vertical axis, they're actually facing you in that point. This would be like actually citing from this side or this direction. That would put the carbons away from you. Chlorine in that case, this is where, again, reach in. Right hand, I'm going to hold with my chlorine. Left hand, grab in is my hydrogen down into the page. Hydrogen's back here. That would put the hydrogen in this position and puts the chlorine over here in this position here, right? So that's one way to do it, is you think about, I have to change my perspective of where I'm viewing the cycle in order to look at it. The other option would be to redraw or rotate the bond, right? So if I started off with the carboxylic acid like this bond being your methyl, and then over here being your chlorine, what I could do is rotate this bond so that I have that kind of fully eclipsing structure. I'm going to sort of set it up so that it's kind of curled around on itself this way. That's that long carbon chain in that direction. Carbonyl up here at the top, and the carboxylic acid down here at the bottom. Now, I did not change this center. This methyl is still in position, but by rotating this bond, swinging the carboxylic acid over this position, the chlorine will rotate back over here. So one of the things you notice is the methyl is a dash, the chlorine is a dash in this conformation. They are on the same side, and that's what we're seeing over here too. The methyl and the chlorine are on the same side of the molecule that we'd have. Once I've got it curled around here, it would be like viewing from this side or from this side. Once it's in this conformation, I'm sort of commonly going down this point. So either of these 2 methods are possible. Either start from your wedge dash structure in that normal extended conformation. Remember, which position, which site you look at each carbon as you move down the chain may change sides, top and bottom, if they're extended structure. Or redraw it in a different conformation that puts it in this position so you can sort of walk down each bond one at a time. Whatever perspective works better for you in that point. So in this structure here, that would place in the structure carbonyl of the aldehyde up at the top, carboxylic acid in the bottom. On the right-hand side for both of them is your methyl and your chlorine, and then the other sides are your 2 hydrogens. Now that's that particular geometry of this structure. Now to go the other way, going from here back, remember we're looking at this structure. This is in this kind of extended structure where if we were looking at the carbon chain moving down, the entire structure sort of curled away from us, right? Top and bottom is always going to be in that extended structure. So for this guy here, we start off, we've got an ethyl and a methyl down here. We have 1, 2, 3 more carbons, and it's OH all along the right side, hydrogens along the left side, like this. How many carbons, quickly viewing this, how many carbons do you have in this chain? You have 2 up here, 1 down here, 3 overall, plus 1, 2, 3. There are 6. This is a C6 molecule at this point. So this is the first thing you should be able to recognize from this, is each one of these crosses denotes another asymmetric center or another tetrahedral carbon, right, as we go down the chain. Okay, to convert back and forth, like we said, we have 6 in that place, so you could kind of think of this as I have, if I've got 1, 2, 3 asymmetric centers, I need 1, 2, 3 asymmetric centers here. Those are the 3 centers I'm converting to. I have an ethyl up at the top, methyl down at the bottom, right? That's that sort of point. So I'm tipping this molecule to the side. Each of these going to the back on the same side of this sort of bent around sort of structure. If I were to take the Fischer structure I have here, I'm going to pick it up and I'm going to twist it over, lay it down to my right. So I'm going to move it over to the right, which will give me this sort of structure here. Remember, that's where I'll have here is I'm pushing the oxygen into the page, and they're all going to be in this kind of eclipsing structure where they're kind of bent around. All those oxygens would be on the same side relative to each other. So this would give me the right presentation. Typically not how we'd end up drawing it though. Usually we'd want to draw this in such a way where we've got some kind of an extended structure, right? That's just generally, it's better to present this in such a way where we have the structure sort of extended out in the lowest energy conformation. So first way to do this is, okay, the first center that we have here, that corresponds to this center here. If we extend the structure out, when they're in that eclipsing conformation, they're all on the same side. When we open it up, they will be on opposite sides, right? Each side, it'll end up sort of switching front and back, side to side like this. If we do this, when we actually sort of, when we extend it to its more stable staggered type structure, right? So here, when we have them wrapped around themselves, you can clearly see that all of these have the same sort of presentation. When we rotate these bonds to give us our more stable structure, they'll end up having this kind of opened up point right here. So this is one of the presentations that you can go through. First, we draw this as it is. We're actually depicting this in the Fischer structure is actually depicting this in this kind of higher energy conformation. Once we've got that sort of wrapped around conformation, we're going to rotate, extend those bonds to give us this longer one. If you don't see this point too, that's where your model kit is really, really helpful. Going from your Fischer projection, you build your carbon chain. In this case, we've got that 6 carbon chain down the line. Ethyl at the top, we have oxygen, oxygen, oxygen down where we have this, again, this kind of eclipsing conformation, and then you can extend it. And you'll see that when we do this, when we go to our line bond structure, the structure is actually going to extend out. This is where we go from here, and we rotate those bonds. We'll end up with first oxygen will be away from us. The second oxygen in this now extended structure will be towards us, and then away from us again. So each carbon will have this kind of opposite geometry visually just based on how it's presented. And again, that's only just based on conformational rotations and manipulations. This is one thing you can see though, is if you actually, when you go to build these, every single center, every second center will have this, it's coming from the opposite presentation. You can also do this if I wanted, let's say, from this structure, ethyl and methyl, 1, 2, 3, OH, 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 H, H, H. You can start off by drawing specifically your first center. So I'm going to start by starting right here. That's this guy right here. I start off by drawing it where I want these two groups facing away from me. It's almost like I'm imagining looking at it from the top. In which case, up here at the top is my ethyl group, and then the rest of the chain is going to extend out in this direction. Now from here, I'm going to have two groups. One is here and one is there, right? In these two positions. Now if the ethyl group is now over here on my left, that means the hydrogen will be here, the oxygen is here. That's the direction I've sort of twisted and rotated the two. Now I want to draw this as an extended structure. I want to continue on this sort of chain. And since I have 2, 3 centers, carbon 2 is here, carbon 3 up over here. And because I want to draw this out in this extended structure, each of these is going to have these kinds of points like this. It's going to terminate with a methyl. So I'm just filling in the wedge dash structures that must be at those two other asymmetric centers. Now, because we've got this extended, you imagine you're looking at this carbon from this perspective. It's still this same carbon, but your just perspective has now changed. If I'm viewing it from this one here, right, imagine that these are away from you, side to side. That's why you're looking at it from this geometry. In that case, OH would be here, and the hydrogen is to the back, right? So what you're doing here is just by changing it, or by extending the structure like this, you're changing the perspective that you're representing that structure, right? So the first one on this side here is to the back. It's on the same side, but next carbon over, it will have an opposite geometry. It'll go to the other side of our extended structure. Third one, we're looking at this blue one. Now we're viewing it from this top perspective here. That will be our OH, and hydrogen is back. And the third one here, hydrogen is up front, OH is the back. What you'll notice is every second carbon, we're on this sort of point right here, they are going to be on the same side of this extended structure when we have that part out. So you can also start by going directly to this structure, just remembering that when we view it in the Fischer projection like this, we're going to be looking at it every second carbon, top, bottom, as we move through this, this geometry. Okay, so now what we're going to do is fill in the structure that you see here. So we have a phenyl group, we have a carbon with a nitrogen on it with an S configuration, and then we have two carbons away, a carbon with a methyl and an OH. Okay. Now there's two different pieces. So what I'm going to do here is start off by actually abbreviating this a bit to make it a little bit easier on us. We have 3 carbons long. We have our NH2, and we have our methyl in this conformation here, and OH. Now, first thing, to make it a little bit easier on ourselves, typically for Fischer projections, usually in a Fischer projection, the convention is to have a carbon chain extended straight out, right? We have a carbon chain directly top and bottom. So one of the things you may see is that because this methyl is not sitting in that sort of collinear, the long chain right here has this oxygen terminating here, a typical thing might be to do is to first rotate this bond to put it into the plane. The other thing too is to make it a little easier on ourselves, instead of drawing out this benzene ring, I'm going to abbreviate that with the terminology pH for phenyl. So the other way to draw this, we've got a phenyl ring here, we have our NH2 at this position, down to the next, up, and instead of drawing the methyl in that position, I'm going to rotate this so this methyl goes into the plane of the page, right? The methyl would be here. If I did that, this is oxygen over here. If you're ever unsure about a manipulation like a rotation, if you've got the right configuration, remember we said this is going to be an S center. Nitrogen is 1. This carbon here would be number 2, 3, and to the back, my hydrogen. That's my S geometry at that center. We said over here, this one had an R configuration. We can check that. That's 1, this would be 2, this is 3. Coming towards us is our hydrogen, and this appears to be an S. Lowest configuration, number 4 here, is towards us. This is still an R configuration. So if you're ever unsure about a manipulation, go back to your SR notation. You can confirm any time you redraw the structure if you've drawn it correctly, because there should not be a change in the configuration of the centers that you're evaluating. All right, so what we've done now is we have a carbon chain nicely collinear with each other. It starts with carbon on this side, ends with carbon on that side. So when we go to our Fischer projection now, we're going to have our phenyl up at the top. We have 1, 2, 3 carbons, so we're going to have 1, 2, 3 crosses, and we're going to end with methyl down here on the bottom. Okay. Now, starting at the top, you're viewing this carbon right here. That's going to have a nitrogen on one side, hydrogen on the other, and the chain is going to extend top and bottom. So this is this first center we're looking at right here. Nitrogen, if I was going to pick this up, I would grab with my right hand, I'm reaching into the page to grab the hydrogen. Left hand, I'm grabbing the nitrogen. I pick it up and I look at that one center. The nitrogen, and H2 is over here. Actually, better to draw that as NH2, right? Showing that you've got a bonding from the carbon to the nitrogen, and hydrogen over here. If you ever want to double check yourself, do your configuration. This is a 1, that's 2, this is 3. We said it's an S center, so it should still be an S center over here. 1, 2, skip it, is 3. This looks like it's R, lowest priority group is towards you. It is still an S center, so we're good. We drew it correctly. Next carbon, right? If we go over one carbon, if we go over one carbon to this center here, there is only hydrogen and hydrogen attaching to it. That one should be pretty quick to do because there's no other groups attaching. It's not an asymmetric center, so we just fill in our hydrogens there. Now we're back to this center right here. Again, we'd be viewing it from the top here. That's how we have the carbon chain facing away from us. That puts the oxygen. I'd reach into the page with my right hand, grab the oxygen, reach into the page, or grab the hydrogen with my left hand, and I hold them up. I will have a hydrogen here, and I will have an OH over there. Again, we can check the configuration to that center. 1 on oxygen. The carbon chain here is 2. Methyl is number 3. Hydrogen is 4. So counting down, this appears to have from 1, 2, skipping over to number 3. This appears to have a configuration that is R. The lowest priority group is towards you. That is it appears to have an S center, but since the lowest priority group is towards you, this is an R center at that position. Okay. So these are the sort of the pieces that we work through as we sort of fill in these kinds of diagrams, right? Number 1 to do is get the chain laid out in this kind of configuration. Number 2, identify which carbon is where along your chain, right? So we have the S center just next to the phenyl, we have a CH2, and then at the bottom we have an R center there. No matter how you draw your configuration, even if you didn't do that manipulation where the methyl group was sort of in that collinear, that vertical kind of axis, it'll still show as an R center. It would not be incorrect to draw, let's say, the oxygen at that lower position, and then the methyl would actually be over on your left-hand side, if you were to look at it that particular way. It's still going to be an R center because all we're doing to move between them is doing a conformational rotation. We're just bending or moving a sigma bond. We're not changing the configuration of that center at all. So one of the values of this, of Fischer projection, is it allows us to very quickly look at two molecules and pick the identity or the relationship between two of them. It's easy to see enantiomers, diastereomers, or identical molecules quickly this way. It also allows us to pick meso compounds pretty quickly too, because it locks us into a single conformation. So if you look at these two, molecule on the left, molecule on the right. First, just consider the molecule on the right, for example. Is it chiral? Okay, I'd say yes, it's chiral because it has a carbon here that has different priorities, 4 different groups. It also has a carbon here. So we have 2 asymmetric centers. The molecule is chiral. I would say this is chiral. More importantly, the molecule is chiral, and notice there's no plane of symmetry in this molecule, right? The methyl's on one side, methyl's on the other, oxygen's top and bottom. It's close, right? There's almost a symmetry. Oxygen's top and bottom, but the methyls are in different positions. So this is not, there's no plane of symmetry. It has asymmetric centers. It is a chiral molecule. Okay, so this molecule here, if you notice, going from the one on the right to the one on the left, the only thing that's different is the position of this methyl group. It's switched. But this methyl group is in the same position. So, are they mirror images to each other? Are they enantiomers? No, they're not, right? If we put a mirror plane here, this methyl is in the same position. Oxygen, same position. Oxygen down here, same position. This methyl has switched. It's a different position. If you go through and do the assignment, what you'll notice is this center here, priority 1 is our oxygen. Priority 2, this carbon group, priority 3, this carbon group. 1, 2, 3. This appears to have a counterclockwise rotation, right? 1, 2, 3. Hydrogen's towards you. This is currently an R center. Over here, though, this is an S center, where this center on top is common between both. These two are not mirror images. They are diastereomers to each other, right? Oops. They're diastereomers to each other. And we can tell that because one center is common, one center is different. One center has changed configuration. Back to the other question we talked at the beginning. The molecule on the right is chiral. It has asymmetric centers, no internal plane of symmetry. The molecule on the left is a stereoisomer of the molecule on the right. It is its diastereomer. One center has changed, not the other one. Last thing, though, is this guy chiral. It's got an asymmetric center, but notice we have a plane of symmetry down the molecule. The top and bottom half are identical, right? This molecule it made it that far where it has asymmetric centers, but it has a plane of symmetry. This guy is meso. This is achiral. The molecule on the left is achiral. The molecule on the left, although, is a stereoisomer of the molecule on the right. And this is where we use these terminologies. Terminology like stereoisomer, diastereomer, and enantiomer is comparing between two. These guys are diastereomers to each other. Properties like meso, achiral, chiral are properties of a single molecule. The molecule on the left is meso. The molecule on the left is achiral. The molecule on the right is chiral. Okay? That's how we use these terminologies. And again, one of the values of the Fischer projection is because we're locked into a single conformation, it's a little bit easier to see that symmetry in these structures. It's also easier to compare quickly between two. And these guys are diastereomers based on the presentations we have. All right, guys, thanks so much. Hope you have a great rest of your weekend. So that's sort of the two different ways of sort of thinking about this. Either we've got our line bond structure and this extended one, and from there you could view this where either bond by bond you're sort of viewing from whatever presentation gives you the proper sort of Fischer structure. What I mean by that is that we need to look at any carbon such that the vertical axis, they're facing away from us. The two other bonds are sort of up to either side of our head, and we'd be looking at that point. So in this case here, in this geometry, I could convert to a Fischer structure by looking down at this bond here. In that case, the nitrogen would be to my left-hand side, and the hydrogen to the right, as long as the carbon chain up and down on the vertical plane. In this one here, to this point here, because of the shape of this bond, I'd have to view it from the bottom down here. That puts these two, the carbon chain is still facing away from me. The methyl then would be on my right-hand side, hydrogen would be on my left. So when we have this sort of extended zigzag type structure, you're viewing it sort of each carbon or each asymmetric center from an opposite face, or redraw it so that it's in this eclipsing type structure. Now you're viewing everything from the same presentation. Top here, top versus here, top here. Both of these two conformations correspond to that same Fischer structure shown over there. Okay, so let's practice this a bit. Here we have this structure. We're giving it to you both in the normal sort of zigzag structure, or if we rotate this bond, we get the structure shown over here, right? This is where we're sort of rolling it around on itself. Makes it a little bit easier to that point. But I'm going to start doing this from the line bond structure in the lowest energy conformation, the one over here. So we have a carbonyl, this is our aldehyde, then over to our methyl group, and then we have our chlorine, and then carboxylic acid terminating it at that position. Now to get to the Fischer structure, we have 1, 2, 3, 4 carbons. That corresponds to our carbonyl up here at the top, and 1, 2 more in the middle, and carboxylic acid at the bottom. So that's our 1, 2, 3, 4 carbons representing here. Right, so that's the first way we do is we set up our template at this point. Okay, carbon number 2 over here. This is the first one we're going to evaluate. Since it's already set up where the two bonds are sort of away from us, if we view it from this presentation, that would be the linear, that's sort of the vertical axis one, that's the carbon chain extending here and here. And if we view it from this presentation, that means that the methyl group would be over here on the right-hand side, putting the hydrogen over on the left, right? So that's where we're viewing it, where this hydrogen here must be this position, and I'm looking at that center in that point. So let's imagine if you picked up the whole structure, right hand on my methyl group, left hand on the hydrogen, pick it up and look at it where the carbon chain is along the vertical axis, matching along, parallel with my body. Now, from here, moving to the next one, I know I'm going to have a center with the chlorine on it, but I cannot view it from this presentation. Then if I looked at it from this angle, these two groups are sort of facing me. It's not the right presentation to be coming out of the plane of the page at me. So I need to look at it from this side here. And if I do that, what you'll notice is, okay, at this carbon, that's the one I'm now sighting on, the chlorine here coming up towards me is in my right hand. Chlorine will be over here. The hydrogen going into the page from this point here is in my left hand. And once again, the bond axis is top and bottom like that, right? Now in that point, what you'll notice though is that in this extended structure, right, where we're in our staggered one, methyl was back, next carbon over, chlorine is forward. That is the presentation we get once you rotate them around. If I were to rotate this bond into that eclipsing structure, they would both be on the same side. They both be dashed relative to each other. When it's extended like this, they show up as opposite sides in the extended structure. But in the Fischer projection, that makes that part clear. That's sort of when we're locked into this single conformation. And we have this geometry over here. That's our final structure. So let's do this one more time, going from a Fischer projection down to our wedge and dash. Now, in the same way, remember, the Fischer projection, what we have here is our ethyl group, methyl group, and we have 1, 2, 3 crosses, OH, all the way down this structure over here in hydrogens. First thing you should be able to recognize is there are 2 carbons here. This is 3, 4, 5, and then 1 down here. This is a carbon 6. There's 6 carbons in this structure here. So one thing I could do is I have an ethyl group at one point. That's my chain terminus. I'm going to draw like a bond. That's this first structure here, is this one here. And I'm going to have a total of 1, 2, 3, which corresponds to 1, 2, 3 centers terminating in my methyl group, like that. In this geometry, if I extend it in this extended structure here, remember what you're also saying is that I'm viewing each of these from some opposite face. So if I have an extended structure, it's like I'm doing a Fischer projection individually from these different perspectives for each center. Again, it'd be fine to draw this as the sort of the eclipsing structure first. You could draw this as, let's say, ethyl to my first center being here, and then I'm going to draw my second center here, and then follow that by my third center here. That would also be fine if you're more comfortable sort of drawing it originally in that sort of this geometry. That's the direct sort of correspondence of going from a Fischer projection to 2D, but I'm going to jump over, try and do it directly to my line bond structure like this, where it's extended. All right, so the first one, the blue center here, I'm looking at it from the top. If I were to do that, right, so what you're doing is rotating this whole thing 90 degrees over, so you're lining it up so it's left to right instead of top to bottom. Ethyl is now over on the left-hand side, and if I do that, going back into the page from that perspective would be my OH. Up here at the top is my hydrogen, right? You don't have to draw the hydrogen, most of it, but I'm just showing both to show you the tetrahedral center. Okay, moving to the next carbon, this one right here. I'd be viewing it from the bottom. Once again, if imagine this such that the center, we have our tetrahedral center like this, and from this perspective, right, from this bottom sort of geometry down here, I would have my OH towards me, hydrogen is away. That's just based on if you were to view this center in that position, because we have a different presentation of where the bonding or where the carbon structure is. It's going to look like it's on the opposite side relative to the oxygen over here. That's because we've got this extended structure as opposed to being in this kind of eclipsing structure that we would normally have. We're showing in the Fischer bond or Fischer projection. Last center, once again, we have, it's going to be another tetrahedral center, so we can put in our 2 groups. The oxygen will be back here, hydrogen's over there. And again, that's just following through this different presentation. So one thing you'll notice is that in the Fischer projection, if these are all on the same side, as we move down the line bond structure and the extended one, they will show up as opposite sides, right? Forward, away, like that. That's a consequence of once we take the Fischer projection and we extend it out, when we sort of roll it out to this point too. So that's how I like to work through this part here. Again, your model kit can really help you with this. If you want, you can present it first like this. This would be in our fully eclipsing structure, where what we have, you can see clearly that every one of those oxygens is away from you when we have the structure wrapped around like this. We could take that structure and then do a rotation, right? We could take this structure, rotate about the bonds into that linear sort of zigzag type structure, and when we do that, having them all sort of to the back when they're sort of curled around, when we extend it around, we're going to get this opposite facing, oxygen back, oxygen forward, oxygen back as we move through that structure. One thing though that really helps you with this is the presentation of R and S, right? If we are going through and we're drawing from a Fischer structure to a line bond and back and forth, you can always check, is the structure R, and is it still R when you redraw them? Changing perspective does not change conformation. In other words, for example, in this case here, we have two asymmetric centers, one is S and one is R. And if you notice, in the 2D structure, we've defined this, that is an S center. The nitrogen is priority 1, the phenyl is priority number 2, the CH2 on the other side is priority 3. That means that this center here has an S geometry. Likewise, this has an R geometry. To double check ourselves when we're done, it should still have an S geometry here. It should still have an R geometry at that position once we're finished, right? So we can always use the absolute configuration to check and see, did I put things in the right position? If it was S, it should still be S, even as we change these perspectives. It does not change configuration by going to a Fischer projection. So just to sort of finish this guy off here, this molecule, NH2, I'm going to abbreviate the phenyl ring as our pH. That just makes it easier for drawing. Next, we've got a methyl group right here and an OH. So as presented right now, we have an R center here and we have an S center here. Going to our Fischer projection, we have a phenyl up at the top. Next bond, we've got, that next bond is this center right here. We've got another carbon right here, that's this one. So that's why we have another cross at that position. And then finally, we have one more here, that's this R center, one more cross there, and we're going to terminate it based on how it's drawn right here. I'm actually going to terminate this with this OH, right? That's what's in the plane as drawn over here. All right, so first center here. If we assign this as, oh look, this is an S center, one thing we can use that to sort of help us. If I was to view this from this top position, right? So the viewpoint I'm doing here is from this top geometry. In that case, if I were to do that, the nitrogen will be over here on my left-hand side, and the hydrogen will be over here on the right-hand side. And to double check it, as we've done here, number 1 is going to be my nitrogen. Number 2 priority is the phenyl. Number 3 is the rest of the chain. Number 4 is the hydrogen. Counting down, 1, 2, 3, this appears, it looks like it's R, but lowest priority group is towards you. This is an S center, so we've done this correctly. It is assigned as an S center over here. It's still an S center when we complete our molecule. So we've done that geometry. That's our double check. Next bond over is just hydrogens. There's no chirality there. It's not an asymmetric center, so we don't have to do anything else. The last center, as drawn, we've got a methyl and an oxygen. The presentation I've done here, I'd be viewing it again from the top. The oxygen's to the bottom. That would put the methyl over here and hydrogen over there. And again, to double check this, we've assigned this originally as an R center. Number 1 is our oxygen. Number 2 would actually be our ring, like the rest of the chain. Number 3 is the methyl, and 4 again is the hydrogen. So right here, 1, skip over to number 2, to 3. This appears. It looks counterclockwise, it looks S, but it's an R center, once again, because the lowest priority group is currently in the page. And that again matches the R center we've designated before too, right? Now, one of the other things, last thing I want to quickly touch on here, a lot of the times what we can do with Fischer projections is by default, What they like to do is extend them off so that the carbons are in the collinear chain along this kind of axis. Now what that would mean is the methyl group over here, we're actually going to rotate this bond, and we're going to do it such that the oxygen ends up in one of the horizontal planes. And we want to do this so that we don't end up inverting the configuration, right? If we would do this point, we want to make sure that we're not, all we're doing is a rotation about this bond, right? So the nitrogen, NH2, will still be over here. We haven't changed it. There's hydrogen. These two are hydrogens. Now if we rotate this bond, right, what we're doing is we're going to just put this so that the methyl over here ends up in the plane. And if we were to do that, the oxygen should actually end up in a dashed type position. So from that perspective, the oxygen would be over here on this side and hydrogen over there. To double check that we've done this correctly, that will be number 1. This chain is still number 2. Methyl is still number 3. That's still number 4. If you look at this perspective, 1, 2, 3, it looks still like it's an S center. It's a counterclockwise rotation. But since the lowest priority group is still in that position facing us, this is still an R1. So even after doing this rotation where we put the methyl group now in the extended chain, oxygen pops up over here. That's kind of all we're doing is we're rotating about the sigma bond back here. We haven't changed the configuration, we've just changed the conformation of the ring. It still is an R center. So that's why these RS notations are so powerful. It allows you to go through and double check to make sure that just by redrawing them you haven't changed configuration anywhere. Okay? So last thing we want to talk about. Fischer projections like this are very good for quickly looking at relationships between two molecules. So if we asked you what is the relationship between these two molecules, what's their properties, we should be able to visually pick it up quickly. So before we jump into that, let's just go back to some of our naming before and under definitions. Look at the molecule on the right. Is that molecule chiral? So stepping back, does it have asymmetric centers? And you should be able to identify that it has 1, 2 asymmetric centers. So yes, it passes. It is not, it has asymmetric centers, it could be chiral. Does it have a plane of symmetry? In this molecule, remember here, top and bottom, no, in fact it does not. One of the nice things about Fischer projections is we've locked into a single conformation which makes this symmetry check very easily. So you can see that yes, it's close, right? There's an oxygen on the top, there's an oxygen on the bottom, but the methyls are on opposite sides of that ring presentation. It's not a mirror image, but look at the guy on the left. Those methyls are in the same position. These guys here, there is a mirror plane, top and bottom. So this is one way we can spot very quickly meso compounds. The guy on the left has asymmetric centers, but a plane of symmetry. It's a meso compound. It is achiral. The guy on the right has asymmetric centers, no plane of symmetry. It is chiral. Okay, so that's just the single property ones. We're not answering the big question yet. We're saying individually consider each of them. The guy on the right is chiral. The guy on the left is achiral. It is a meso compound. And we can see that clearly by this Fischer presentation. It's one of the values of the Fischer presentation is because we lock into a single conformation, it makes that check quite quick, quite easy. All right. Now, what's the relationship? Okay, top carbon over here is has the methyl over to the right. This top carbon, same configuration. If it's R in one, it'll be R in the other, right? That's what we're really saying. The second carbon, though, is methyl to the left, methyl to the right. It's different at that carbon. In other words, one of the two centers is the same S or R configuration. The other one changes. One is the same, one is different. They are not mirror images. They are, in fact, diastereomers to each other. So just baked into this, there's a bunch of different points we can look at. Individually, molecule by molecule, the guy on the right is chiral, has asymmetric centers. The guy on the left is achiral, has asymmetric centers, but is meso, has a plane of symmetry. What are they to each other? They are diastereomers to each other. One center is common, one center is different. They are not mirror images to each other. Okay? That's how we would sort of complete this sort of analysis. All right, guys, that's the end of this point. I hope you guys have a great rest of your weekend. I will talk to you guys next week.